Hello students, welcome to physics class. In the last lecture, we have learned the behavior of conductors in an electric field. Today, we will discuss capacitance and capacitors. So, let us begin. We know that when charge is given to a conductor, it gets distributed throughout its surface. Hence, conductors have an ability to store charges. This is of great practical importance. By storing charge, actually we are storing electrical energy. This stored energy can be converted to other forms such as light, sound, mechanical energy, etc. as and when needed. The ability of a conductor to store charge is measured in terms of its capacitance or capacity. When a charge is given to an insulated conductor, the electric field in the region around the conductor increases. To put more charges on the conductor, more work has to be done against the electric field, and hence potential also increases. Therefore, as charge increases, electric field increases, work done increases, and hence potential also increases. So, potential is proportional to charge, or charge is proportional to potential. Mathematically, Q is proportional to V, or Q is equal to C multiplied by V, where C is a constant of proportionality and is called capacitance. So we get C is equal to Q divided by V. Hence, capacitance is defined as the ratio of charge to potential of a conductor. If potential is equal to 1 volt, then C is equal to Q. Thus, capacitance of a conductor is numerically equal to the charge required to raise its potential by 1 volt. The SI unit of capacitance is farad. 1 farad is equal to 1 coulomb per 1 volt, or capacitance of a conductor is said to be 1 farad when 1 coulomb of charge raises the potential of conductor by 1 volt. The unit farad being large, for practical purposes, smaller units such as millifarad, microfarad, picofarad, etc. are used. Symbol of capacitor is as shown. We have seen that the capacitance is defined as the ratio of charge to potential of a conductor. Let us try to understand the meaning of this equation. The smaller the change in potential due to transfer of charge to a conductor, the greater is the charge that can be put on the conductor, or it has large ability to store charge, or its capacitance is high. But for a given conductor, there is a limitation to store charge, or we can say that the capacitance of an insulated conductor is very small. As the charge increases on a conductor, the potential also increases. High potential difference implies strong electric field around the conductor. The maximum electric field that a dielectric medium can withstand without breakdown of its insulating property is called dielectric strength. For air, this is of the order of 3 into 10 power 6 volt per meter. If the electric field around the conductor crosses this value, the surrounding air break down and it start to conduct. This will cause the charge on the conductor to leak away. Therefore, the charge that can be stored on the conductor is limited to the value such that the electric field is not large enough to cause ionization of surrounding medium, or we can conclude that the capacitance of an isolated conductor is very small. Now let us calculate the capacitance of an isolated spherical conductor. For that, consider an isolated spherical conductor of radius r. The charge Q is uniformly distributed over its entire surface. It can be assumed to be concentrated at the center of the sphere. The potential at any point on the surface of the spherical conductor will be V is equal to 1 by 4 pi epsilon naught Q divided by R. Therefore, the capacitance of the spherical conductor situated in vacuum is C is equal to Q divided by V. Now substitute the value for V and we get C is equal to 4 pi epsilon naught R. Clearly, capacitance of a spherical conductor is directly proportional to its radius. If the sphere is in a medium, then C is equal to 4 pi epsilon naught epsilon R into R. The capacitance of Earth is C is equal to 711 microfarad. That means if we take a spherical conductor of the size that of Earth, its capacitance will be only 711 microfarad. If we want to have a spherical conductor of capacitance 1 farad, its radius must be 9 into 10 power 6 kilometer. This radius is 1500 times the radius of the Earth. So we conclude that 1 farad is a very large unit of capacitance and it is not possible to have a single isolated conductor of very large capacitance. So if we tend to have a single conductor of large capacitance, it will have practically inconvenient large size. But by a suitable arrangement of two conductors separated by an insulating medium, we can store a large amount of electric charge and electric energy. This arrangement is called a capacitor. To understand the principle of capacitor, let us consider an insulating metal plate A. Let some positive charge be given to this plate till its potential becomes maximum. No further potential No further charge can be given to this plate as it would leak out. Now consider another insulated metal plate B held near to plate A. By induction, a negative charge is produced on the nearer surface of B and an equal positive charge develops on the further face of B. This induced negative charge tends to decrease the potential of A and the induced positive charge tends to increase the potential of A. As the induced negative charge is closer to A, it is more effective. The overall potential of A reduces and hence some more charge can be given to A to raise its potential to maximum. Thus, capacity of the conductor A has increased by bringing another uncharged conductor B in its vicinity. Now connect the plate B to earth. The induced positive charge on B being free flows to the earth. The induced negative charge on B however stays on it as it is bound to positive charge on A. Due to the induced negative charge on B, potential of A is greatly reduced. Thus, a large amount of charge can be given to A to raise its potential to the maximum value. Hence, we conclude that the capacitance of an insulated conductor is increased considerably by bringing near it an uncharged earth conductor. This is the principle of capacitor. Such an arrangement of two conductors separated by a dielectric medium is said to form a capacitor or a condenser. The commonly used capacitor is parallel plate capacitor. A parallel plate capacitor consists of two metal plates having surface charge density sigma and area A. If plus Q charge is given to one plate, minus Q charge is induced on the other plate. These two plates are separated by a distance d. We know that there exists an electric field between these two plates and its value is given by sigma by epsilon naught. Therefore, the electric field between the plates is uniform. Therefore, the potential can be written as V is equal to ED. E is equal to sigma by epsilon naught. Therefore, V is equal to sigma by epsilon naught into D. Sigma is the surface charge density and it is given by Q divided by A. Substituting this, we get V is equal to QD divided by A epsilon naught. The capacitance of the parallel plate capacitor C is equal to Q by V. Substitute the value for V, we get C is equal to Q divided by Qd divided by A epsilon naught. By simplification, we get C is equal to epsilon naught A divided by D. If the space between the plates is filled with dielectric medium of relative permittivity epsilon r, then C is given by A epsilon naught epsilon r divided by D. Therefore, the capacitance of a parallel plate capacitor is directly proportional to the area of the plates and inversely proportional to the distance of separation between them. And by using dielectric material of high dielectric constant, we can increase the capacitance of a parallel plate capacitor.